Hi, my name is Manish Gupta, and in this video, I'm going to talk about code-optimized reasoning training, which is basically a method to teach large language models to perform reasoning with tool usage. So let's get started. What are the challenges when integrating coding tools with large language models, right? I mean, these days, tool usage or function calling is very popular, and specifically when it comes to using coding tools, what are the challenges? So before we talk about the challenges, in fact, let's set up the problem setting. So the idea is that you have a initial problem to solve. Let's call the problem as P. You have access to a large language model called as Pi. You have access to a code execution environment or a code tool called as E. And then you also have, at time. So basically, when you have this large language model and the code execution environment, the way it works on top of this problem is to basically, do reasoning in terms of triplets. So these triplets can be represented as N1, P1, O1 or NT, PT, OT more generally for at any point of time T. And after, it basically does these reasoning over these triplets. Finally, it comes up with the answer, right, to the input problem P. Now, what do these triplets mean? So O1 is essentially, the output of or rather, let's talk about first P. So essentially, capital P is the problem itself. And in the beginning, the initial triplet is basically empty. So considering the initial problem, you essentially try to apply the large language model so as to essentially get two things. NT and PT. NT is the textual reasoning component, and PT is the program component that needs to be executed by the coding tool. So you take this program component and get it executed by the coding tool so as to get the output OT. Okay. So basically, at any point of time T, NT is essentially the text reasoning kind of thought process. In that sense, PT is the program to be executed, and OT is actually the output of the program. After the program is executed by the coding tool. Okay. Now, obviously, the next thought basically is generated by considering the thought so far, the chain so far, concatenating that with the textual reasoning, part of the thought, and then the program, and then the execution output of the program. Now, when you try to do these kinds of things using large language models, one of the ways of doing that is as follows. So you see this problem at the bottom. It's a mathematical problem, each phase of two non-congruent parallelepipes and so on. There's a complicated math problem. To be able to solve this problem, one of the ways is to essentially just do what is called as prompt hinting. So you take a large reasoning model like DeepSeek R1, and essentially just immediately after the think token, you basically add this green prompt. That's basically a prompt hint telling it to actually use code tools. To motivate the model to use code tools, this is what you can do. Okay, let's try to solve this problem step by step using multiple Python code calls. Now that's basically the tool usage prompt in that sense, right? And then, well, I mean, the model actually does a whole bunch of thinking, the text-based thinking and the code-based thinking, generates programs, outputs the, executes the program to get the output, uses those outputs so as to essentially think more, and finally lead to the final answer after the thinking is all done. Okay. Now, there are some issues, some problems while doing this kind of stuff. First, when it basically tries to make use of this tool, there could be a conflict between the large language model's own internal probabilistic reasoning and the external, deterministic output that is generated by these code interpreters or code tools. Okay. So basically, when you want to solve a problem, there is a large language model way of doing it by using the internal probabilistic thinking by the LLM, and there is an external deterministic way of doing it using Python tool, right? So there's a conflict between the two. In fact, this conflict leads to two interesting phenomena when using code tools with large language models. Delayed code computation. So typically LLMs prefer to do text-based reasoning rather than utilize a code interpreter. And second, code result distrust. So even after it basically gets the result from the code interpreter, it does not think about it as a deterministic knowledge, but actually it just unnecessarily keeps verifying the code interpreter's outputs manually, right? And that's basically some problems when you try to use these simple prompt hint kind of a technique, basically just telling the model to think step by step using multiple Python code calls. Okay. So we will basically refer to the model, which is so what the authors did was to essentially take a DeepSeek R1 distilled Quen 32 billion parameter model. So it's a large 32 billion parameter model. And then the supervised fine-tuned it on this kind of, this kind of data, 800 samples of this kind of data, where the problems were taken from still3 dataset. Okay. So they took those still3 dataset problems, used the DeepSeek R1 model, which is a much larger model, right? so as to essentially do this prompt hint annotation. So basically just add this thing after the thing step and essentially get the output. So whatever output you get, you take that output, the input problem and the output reasoning trace, and you essentially reasoning and the answer, everything, right? And then you distill, and then you supervise fine tune this 32 billion parameter model. So that gives you your prompt hint supervised fine tuning 32 billion parameter model. But that suffers from these kinds of problems. Okay? So how can you make it better? How can you make the tool call usage with large language models better? Coding tool call usage with large language models, right? So that is why these authors, introduce this technique called as CoRT, or code optimized reasoning training. Okay, so the CoRT method works as follows, as is shown in this top diagram. Okay, so it's basically a post-training method to teach the large reasoning models to effectively utilize the code interpreter tools. Okay. So in fact, there are two steps, as you see. The upper one is for frontier models, large models, and the lower one is for lightweight models, like a 1.5 billion parameter model. Okay. So in the upper part, you see there are multiple stages. So in the first stage, you do hint engineering, or other, you basically do cold start, and the cold start phase is actually called as hint engineering. We'll talk in detail about that. Then you actually do rejection fine tuning using rejection sampling in that senses. Further, you do so that basically gives you a hint engineered rejection fine tuned model. Okay, so that's that. Now that's still a 32 billion parameter model, because in this part, you basically deal with 32 billion parameter models. Then in lightweight model part, you deal with 1.5 billion parameter models. So you start with a 1.5 billion parameter model, you distill it from a 32 billion parameter model, you do reinforcement learning to make it better, and that gives you your hint engineered reinforcement learning based 1.5 billion parameter model. Now let's talk about each of these stages in detail one by one in this slide. Okay. So the first stage is this cold start stage, or the hint engineer stage. Okay. So compared to the simple prompt hinting, where you essentially just add this green part, okay, let's try to solve this problem step by step using multiple Python calls. Compared to that, you actually add multiple hints all across the reasoning path. So rather than just giving one hint at the beginning, which you do anyway, you actually give multiple hints on the path. See these green things? These are all hints, basically. Okay. In fact, they add two kinds of hints to solve the two problems that we talked about on the previous slide: delayed code computation problem and the code result distrust problem. So for solving the delayed code computation problem, whenever they observe that the model is actually trying to force fit a text-based reasoning chain rather than using a Python-based program, they basically add this thing. It looks tedious, and we can use Python code to simplify the reasoning and then leave it with a Python prompt so that it actually outputs Python code. Okay. There are other variants of this that can be also added, like let's compute V1 and V2 using Python for accuracy. Okay. So that's that. So and the second thing is basically they try to solve the code result distrust problem. So after the result has been obtained, they basically add this nice little hint saying we don't need to doubt the accuracy of Python calculations. Okay, so as to avoid unnecessary reflection and unnecessary verification of the output generated by the coding tool. Okay. So they tried to do this kind of stuff automatically, but they found that automatic injection of delayed code computation, automatic decision of where to inject these prompts was difficult. And therefore, they manually curated 30 high quality samples. And they took those 30 high quality samples and used it for supervised fine tuning. The stage one part, right? To post train, supervised fine tuning to post train 1.5 billion to 32 billion parameter models. So basically, this part basically gives you a hint engineered SFT 32 billion parameter model. So the output of stage one is this hint engineered SFT 32 billion parameter model. To improve it further, they do rejection fine tuning. So what is rejection fine tuning? Well, they use the same still3 dataset for each of those problems. They actually obtain multiple samples using their hint engineered SFT 32 billion parameter model. And on each of those samples, they actually try to, these samples are trajectories of those triplets. So they try to figure out those trajectories which lead to incorrect final answers or have delayed code computation or code result distrust behaviors. And they try to use them as rejected samples. So that is how rejection sampling is performed. But the rejection sampling is not performed on the hint engineered SFT 32 billion parameter model. Hint engineered SFT 32 billion parameter model is just used to generate multiple samples. The rejection fine tuning is actually performed on the original DeepSeek R1 distill Quen 32 billion parameter model. So you should think, the diagram is sort of confusing. You should really think about it as like the base model is also used to perform the stage two. However, the samples that are used to do rejection fine tuning are obtained from the stage one hint engineering SFT 32 billion parameter model. Okay. Now, once that is done, it basically gives you a hint engineered RFT'd 32 billion parameter model, where RFT basically stands for rejection fine tuning, right? Rejection fine tuning. So you use this model so as to basically do distillation, and you do distillation for both kinds of models. The first model is essentially the prompt hint SFT 32 billion parameter model. So prompt hint SFT is basically this model, right? This model, where the original base model was the same. It's just that it was fine-tuned using prompt hint SFT technique, right? And you also do this distillation on the hint engineered RFT 32 billion parameter model. So you take the hint engineered RFT 32 billion parameter model and you do distillation. You distill it down using a base model, which is this DeepSeek R1 distill Qwen 1.5 billion parameter model. So this blue part really operates in the 1.5 billion parameter regime. Okay. So that gives you two models, 1.5 billion parameter sized, prompt hint 1.5 billion parameter SFT distilled model, and hint engineered SFT 1.5 billion parameter distilled model. Distillation is performed using 10K samples on math reasoning datasets, which are like from public datasets. They obtain these 10K samples. Finally, they perform the stage 3, which is code integrated reinforcement learning. So they perform reinforcement learning using GRPO, the popular, group-based, proximal optimization. So group-based optimization, policy optimization. Group-based policy optimization, and with 4 interesting tweaks. One, while doing this reinforcement learning, they put a max tool usage limit T. So I think they put it as 15. So maximum number of times that you can call the tool is like 15 times. And they append the hint to discourage tool usage beyond that max limit. So once it reaches that max limit, they basically just add a hint to discourage tool usage. Second, the code environment that is used is basically a persistent Jupyter-like execution environment, so that it has access to variables and output from the previous execution of the code, so as to make it more optimized and more lesser token usage in that sense. Third, they also perform execution result masking to avoid model collapse. So, what could happen is that if there is a whole bunch of tool usage, then the model may actually lose its power to, or strength to do reasoning, its own textual reasoning. So as to avoid losing that strength, essentially they sometimes, for some of those samples, they mask out a few tokens from the execution result so as to avoid this model collapse, right? And the fourth thing that they do is to basically the rewards that are used for this GRPO. Well, they basically use 2 rewards: answer correctness score. So obviously the answer should be correct. And the second, which is a binary reward. And the other one is a code execution reward, which basically is also a binary reward, but it basically is like, hey, whether the code was executed correctly or not, right? So, so they give higher weightage to answer correctness, just a 10% weightage to the code execution reward in that sense. So that's basically how the code optimized reasoning training work. Now, how does it perform? So if you look at this table, let's look at this table, okay? So there are various models. There are state-of-the-art models for these different math reasoning data sets. So there are several 5 different math reasoning data sets that you see, and there's an average at the end, okay? So there's these state-of-the-art models, O1, O3, O4 mini, and so on. And there's also this Alibaba's QWQ 32 billion parameter model. Some of them use tools, some of them don't. So basically O3 and O4 mini, basically they are run with the tool usage, and they all perform RL anyway, right? Now, there are these other models, frontier models, 32 billion parameter models that they work with. So essentially, these are DeepSeek, START, Still3, Tool, Retool. These are all standard models that are publicly available. They have trained prompt hint model and hint engineered SFT and RFT models. So, and then they also, experiment with lightweight models, 1.5 billion parameter models, where basically, there are these existing previous work, and there's this prompt hint and hint engineering based models, right? So what do you observe? So you basically observe that across these models, on average, if you look at the accuracies, right? So basically, 81.8 from prompt hint SFT model is actually very close to 82.2, which is basically the best accuracies that you can obtain in the state-of-the-art models, right? And interestingly, the hint engineering model is also 81.3, not very far from 81.8, which is basically the prompt hint based model. Now you might be wondering, hey, big deal. So, what was the point in doing all of this hint engineering when just the simple prompt hint technique, where you basically just add a small little prompt after the think token, gives you almost the same results or even better results on average, in fact, right? So the idea is as follows. Although the results are almost the same, 82.2, 81.8, 81.3, almost the same. The idea is that, efficiency-wise, it reduces token usage significantly. So this prompt hint model, sure, it gives you 81.8. KWQ, sure, it gives you 82.2. But when you look at the reasoning traces of these models, the reasoning trace, the thinking trace is extremely long. Okay. So the interesting part is that CoRT-based training actually reduces token usage by about 30% for 32 billion parameter models and 50% for 1.5 billion parameter model. Okay, this chart actually shows you that. So on the x-axis, there are these average tokens in the result, and on the y-axis is basically the accuracy in some ways on the AI ME24 dataset, one of those math reasoning datasets. And what you observe is that, yes, there are these tools, there are these models like START 32 billion, or well, that has a poor accuracy anyway. But QWQ 32 billion, you see, the accuracy is really nice. It has like 82.2, which is not very high compared to hint engineering RFT 32 billion. But look at the number of tokens. It uses like 14K tokens, while these hint engineering models use like 7K tokens, half of them. Okay. So the idea is that CoRT trained models essentially give you almost the same performance as the SOTA models, the state-of-the-art models, or typical standard code usage-based models, code tool usage-based models, but the token usage is reduced by 30% approximately for 32 billion parameter models and 50% for 1.5 billion parameter models. Okay, so this is also visible in this chart. So you can see inference token budget, which is basically number of tokens in thousands, and the accuracy on the y-axis. And the blue curve is the R1 distilled 32 billion parameter model. The orange curve at the bottom is basically the prompt hint based method, the simple method, and then the red curve at the top is basically their hint engineered RFT 32 billion parameter model. And as you can see, the red curve basically dominates the blue and the orange curves basically. Okay. So what is also observed as part of the reasoning trace, that is, when you look at what the model does, you observe that the prompt hint-based model was using the coding tool mainly for verification. 82.4% times it basically uses it just for verification, right? But it uses code tool only 17.6% of the times for actual calculations. Okay, while the hint engineered model actually does a better job, 51%, almost 50% of the times it's basically using it for calculation, the remaining 50 for verification. Okay, so sort of morphing the code tool usage to more useful nature rather than just for verification purpose. Okay. Also, this is a chart which basically shows you across these models. So hint engineering model is at the end and R1 distill right here, different models that you see here. For each of these models, it basically shows you the average token usage in case of correct responses versus incorrect responses. And you observe that, both in case of correct as well as incorrect responses, the hint engineering models actually take much lesser number of tokens, right? The number of tokens saved are much more when it basically generates incorrect responses. But well, overall, the number of tokens used by the model are significantly lower. Okay. You can also look at how the models use, what kinds of purposes is the code tool used for. When you use the prompt hint-based technique versus the hint engineering technique. Remember, the prompt hint technique is a simple technique where you just add a single prompt right after the think token, while hint engineering technique is that elaborate technique that we discussed in the previous slide. Okay. So you observe that prompt hint technique uses just the verification kind of stuff 51% of the times, while hint engineering is doing property verification, theorem checking like much lesser, 30% of the times, right? Similarly, you would observe that the hint engineering model basically does a whole bunch of calculations, like solving equations, systems of equations, much more frequently compared to the prompt hint-based model. Similarly, you observe here, for example, there is basically just numeric approximation methods are used just 8% of the times, while here numeric approximation methods are used 11.7% of the times, and so on. Okay. So in summary, in this video, I talked about CoRT, which basically involves supervised fine-tuning with hint engineering, and it also involves reinforcement learning, and lastly, it also involves rejection fine-tuning. Right? This hint engineering specifically contributes significantly. It maintains the similar kind of accuracy levels across various math reasoning tasks. However, it reduces token usage by 30 to 50%. It sort of does this by mitigating meaningless reflection behaviors in large language models and motivating tool call usage. Reinforcement learning specifically shapes the code usage behavior toward either efficiency or increased integration of coding tools with the large language model reasoning. Okay, that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.